Hey guys, Mr. Betts here. It is finally time that we get to talk about how we move from average rate of change to instantaneous rate of change. And keep in mind from the last video, you know that instantaneous rate of change means we're finding the slope of the tangent line. So we are solving the tangent line problem here. So let's look at a secant line versus a tangent line. And we know how to solve this problem. We know how to find the slope of a line through 2 points. We have a slope formula. We know how to do that. We do not yet know how to solve this problem, how to find the slope of a line through a single point. So the idea here is we want to know how we get from here to here. So I'm going to put these two graphs on the same coordinate plane and talk about how we can move from this average rate of change, which is the green secant line here, it's the slope of the green secant line, to an instantaneous rate of change, which is going to be the slope of that orange line. So the big idea here is actually a pretty simple one. If I want that green line to become more like the orange line, I'm going to take this point right here and I'm just going to move it closer to the point of tangency. So this, remember, is a point of tangency. And as I move it closer, we can see that that green line is becoming more and more like the orange line. And we can get that those 2 points pretty close together. The question is, how close can I get them? Because it's not really a tangent line until these 2 points are the same thing. Remember, we cannot make them the same thing, but we can get pretty close. And this comes from the idea of limits that we talked about in Unit 1. So what we're going to do here is we're going to take this difference quotient here and we're going to look at how we can analytically move this point closer and closer to that point. So with this difference quotient, I'm going to use the x value of a to kind of anchor this tangent point right here, the point of tangency, and then the other point here I'm going to call x. And the idea here is we want to move this x value here closer and closer to a. And the closer x gets to a, the closer that secant line is to the tangent line. This might sound familiar to you. This is the exact idea that we use with limits. So if I take this difference quotient right here and apply a limit to it and say, okay, let's look at what happens as x approaches a. The idea here is we know x is getting really close to a, but it's never going to equal a. All right, and so the limit gives us this way of dealing with the zero in the denominator that doesn't actually ever become zero. It just gets really close to zero. So we can look at what happens as the secant line approaches the tangent line. I do want to point out that the visual here I'm giving you is x approaching a from the right side, but we could just as easily take this point and approach from the left side. So this would be x approaches a from the left. So this two-sided limit here would give us what happens as a secant line from either side approaches the tangent line. And we should expect that to give us the same value. So the idea here is the secant line is just getting closer and closer to the tangent line. And that's it. That's how we solve the tangent line problem. I do want to look at this in the context of the other difference quotient that we looked at. So in this case, we said this is a, and then this distance from a to the second point for our secant line, that distance is h, giving us the second x value of a plus h. And the idea here is as a plus h is approaching a, that distance is shrinking to zero. So we look at this as the limit as h approaches zero. And just like the last one, the visual here, h is approaching zero from the right because the point is approaching from the right. But we could take the second point here and have a negative h value that's approaching zero from the left. And again, both of those are going to give us the same value. So again, this difference quotient here, as h gets smaller and smaller and smaller, tells us what the secant line is going to look like as it gets closer and closer to the tangent line. So we can use these two things to actually define what we call a derivative. So the instantaneous rate of change of a function at the point x equals a can be expressed by either of these limits on difference quotients. So the first one, again, the distance between the 2 points is approaching zero. The second one, the second point is approaching the first point, what I call the anchor point or the point of tangency. And we're just applying that to a difference quotient that gives us the slope of a secant line. So this right here is the slope of a secant line, but as h gets smaller and smaller and smaller, it becomes the slope of a tangent line. Now, this is important, provided the limit exists. So we say that we can find the instantaneous rate of change if this limit exists, and we can take the derivative. So this defines in calculus what we call the derivative. So it's the derivative of a function at a point, and we use this notation right here. F prime, this apostrophe here, is read as prime. So we say f prime of a gives us the slope of the tangent line. I'm going to be pretty specific here. The slope of the tangent line to the graph of f at x equals a. Okay, so this is the definition of the derivative, which is how we solve the tangent line problem.